In this video, we'll talk about polynomials and the more theoretical reason why we actually care about complex numbers. So one of the main reasons theoretically that mathematicians care about complex numbers is the idea of the Fundamental Theorem of Algebra. And what this theorem says is the following. It says if I have any polynomial, p of z equals 0, of degree n, then it always has exactly n complex solutions if I count for multiplicity, i.e. if I have a double root, I count it twice. So the whole thing of not having solutions and not knowing what they are doesn't exist in the complex numbers. Every polynomial you write will have the correct, as in matching the degree, number of solutions in the complex numbers. There will always be 3 solutions to a cubic. There will always be 4 solutions to a fourth order polynomial. No matter what you write, there will always be that many solutions, assuming you count for repeated roots. What this tells me sort of directly is every quadratic always has 2 solutions. They're either 2 distinct real solutions, 2 complex solutions. We'll talk about why it can't be something in the middle later, or 1 repeated root, i.e. it's something like x minus 4 squared. We're not even thinking about that as a repeated root. It is there twice, so it has 2 solutions, 4 and 4, in this sense here. This also means, for instance, there are 5 complex solutions, some of which might be real. Here's the thing, by complex, I don't mean they have to have a non-zero imaginary part, right? If it has 0 imaginary part, it's basically a real number, and that's okay. It means if I include all complex numbers in my answer, I will have 2 solutions. So the quadratics, or 5 solutions here, to the equation x to the 5th minus 4x cubed plus 3x squared equals 4. With the 4 over to the other side, I have a polynomial equaling 0. There are going to be 5 solutions to that because this is a 5th degree polynomial. What other facts do we have? Well, the other fact that's important to know here is that if the polynomial is a real polynomial, i.e. all of its coefficients are real numbers and not complex, then the complex solutions must come in conjugate pairs. So you write this out saying if p of z is a real polynomial, and by that I mean all coefficients are real numbers, then the complex roots will come in conjugate pairs. What does that mean? Well, that means that if, say, a plus bi is a root, so is a minus bi. If I have some root that's complex, I have to also have its pair as another complex root as well. Because if I don't have that, then my polynomial is not going to be real valued. It's not going to have real coefficients at that point. So for this is why we know we can't have 1 real and 1 complex root for a quadratic equation. Why not? Well, if I had that, since I have 1 root that's not real and it's complex, its conjugate must also be a root. And that's 2 roots, which means I don't have room for a 3rd real root because I only have 2 roots because I'm only a quadratic. This also lets you say things like the following. Every cubic must have at least 1 real root. Why is that? Well, my roots, if they are not real, must come in conjugate pairs. But I only have 3 roots total. So I either have 3 real roots, or I have 1 complex, its conjugate pair, and then my other root has to be real because it can't also be complex. I can't have another conjugate pair to go with it because I only have 3 roots total. And to follow up, if a cubic has 2 real roots, it must then have 3 real roots. You can extend this idea to any odd degree polynomial in the exact same way. The main point is you can never have an odd number of non-real roots because they all have to come in conjugate pairs. And that's really what this idea sort of tells us about polynomials. You get a lot of information out of the fact that you know the roots for a real polynomial have to come in conjugate pairs. It means you can start factoring things easier, you can look for these irreducible quadratics, and build from there. The point is, these conjugate pairs are what give me irreducible quadratics. That's why when we said before that every polynomial can be factored into linears and irreducible quadratics, this is why. It's because those irreducible quadratics will always have roots of being complex conjugate pairs, and that's where that step comes from. So for example, I want to find all solutions to the equation x to the 5th plus x cubed minus x squared minus 1 equals 0. And so we're going to start by trying to manipulate some factors a little bit, and we notice that we can if we look at this being x cubed times x squared plus 1 minus 1 times x squared plus 1 equals 0. We're factoring by grouping here. So I get x cubed minus 1 times x squared plus 1 equals 0. Now I can factor each term individually. X squared plus 1 equals 0. Well, I know what these are. These are just my imaginary units. This is plus and minus I, because those both square to minus 1. For the other set, I have x cubed minus 1 equals 0, or x cubed equals 1. These are my third roots of unity. So I know how this works. I have x is e to the I 2 pi over 3, e to the I 4 pi over 3, and x equals 1. Then my 5 solutions here are x is 1, I minus I, e to the I 2 pi over 3, and e to the I 4 pi over 3. Once you can solve out these problems, looking for things you already know and things you know about can build together to make this all work. The point here is we can break this down into simpler pieces, both the plus or minus I and then the roots of unity, and we also know we should definitely get to 5 solutions. Once we get to 5, we know we're done because we had 50-degree polynomial in the first place. We should get 5, and because we're looking at complex numbers, we know we're going to get 5. And that's the point of the Fundamental Theorem of Algebra, is that I know that I will find 5 solutions here. So it might be repeated. In this case, I didn't have any repeated solutions. But I will always get 5 solutions because of the 3 polynomial. And that's why we care so much about complex numbers, because they let us say this fact. They let us always say we're always going to have the right number of solutions because the complex numbers give us the space we need to always find all the solutions.